What's up, everybody? Welcome to this week's episode of the Well Man's Podcast. My name is Brian Brozy. I'm joined by my friend and co-host Keoni Tita. Keoni, how are you today?
Good, Brian. Hi, everybody. Thanks for listening to us once again. Hopefully, people will get something out of this one. I think it's a very important one. I think it's related to the pandemic that we're currently under, too. We're going to talk about climate change. This is part two. We did one, it was episode 153 on climate change, just kind of as a follow-up to that. And just so you guys know what we're following as kind of resources is an ebook called Human Cause Global Warming, Climate Change, Understanding the Science. It's basically a resource guide for teachers, students, and even policymakers. And it's basically put together by somebody who's really not a climate scientist, but is definitely kind of, an expert in of his own because of all the research that he's done. And his book is just great. It's one of the most concise, easily understandable ebooks on climate change. But you can Google it. His name is Jack Gibbons. He's a friend of the family, so that's why I'm putting it on. He's a professor at Long Island University. Another book that I think is really good for people is called the Drawdown book, The Most Comprehensive Plan to Reverse Global Warming. I think this is really pertinent right now because we have a new administration coming in. We have the Biden administration coming in who is really very taking this serious and is very pro-environment as opposed to, what the previous administration has done. So I'm excited about that because the reason why Brian and I want to do this is because there's a lot of hoaxing out there and, just denying it. And I think it's very easy to deny things when, for example, it's as simple as going out on a winter's day and it's freezing and you're going, how can we have climate change when it's cold out? So in these podcasts, I'm hoping to kind of help get rid of some of the myths around that.
Yeah.
So
The author, Keoni, can you say his name again?
Jack Gibbons,
And
Gibbons.
and then you were kind of alluding to that he's not like a climate scientist, but what is he? But he's researched it a lot.
Yeah, he's put together this ebook for, just as a policy resource guide and for his students and everything like that. So he's a professor to just put it together. But he's not like, a climate scientist working for NASA or anything like that. But the reason why I really like this book is because I've read a number of climate books, and this one just makes it very, very easy to understand. I mean, super, super easy. And once you get a good base, which I'm hoping these podcasts will do, I think people will be able to read the science and really get an idea of how it all makes sense and dispel a lot of the myths out there. So, and in fact, I mean, I'm not certain about this, but I think I actually have more experience than him in climate science, just because of my master's in environmental engineering. However, reading his book, I was just impressed, and I'm hoping we can get him on here at some point to talk about it. And again, you can become an expert in a number of ways, right? You can become an expert by reading a certain topic and being very passionate about it, which I think he was. You can become an expert in just being in academics, which he is. I think he teaches classes like this, probably earth science classes at Long Island University. I'm not certain about that. But
So we're not talking about Alex Jones. That's not where
no,
we got the.
No. We're not. We're certainly not talking about somebody like that who's just denying it and can't back up that denial, right?
Sure. Yeah.
At all. In a reasonable, common sense way.
Yeah. So no matter what the point is, we're getting an educated, well thought out point, is what you're saying.
Well thought out point. Yeah. He is definitely. He's definitely, in academics and the book is written as such, but he wrote it in such a way that I think for the lay person, it's very easy to understand. So,
all right.
So I want to just review episode 153, just real quick. We'll just go through it and then we'll get into the meat of this episode. All right. So to begin, one thing that I always hear, the climate system is extremely complex. So how can you really understand it? Um, it is absolutely true that it's extremely complex, but we have models and things like that, and just common sense science, known science, that we can get a good idea of what is going on. Um, Last episode, we talked about the science is clear, but both on theory and experimentally. Um, and the reason why we're doing it is because I think since we're going through this and everybody on this planet, every living being is on this planet is being affected by it, that people should make an effort to kind of understand it. The other big thing that's going on is with this pandemic. People think that this viral pandemic or the viral pandemics that we had in the past, they don't see the connection to climate change. Well, there's definitely a connection there. A simple connection would be as the earth warms, you get more vectors or bugs or animals moving north, so that can spread disease. Think malaria
Mm,
and mosquitoes moving north and spreading disease.
mm,
So that's
yeah.
one way, right? Um, Another way is with climate change. For example, what happened in Puerto Rico is Puerto Rico got hit by a devastating hurricane. What was it, a couple years back?
Mhm.
They actually still have not completely recovered from that. And then right on the heels of that hurricane comes this pandemic. That hurricane was made a lot worse by climate change, but now because of the viral impact coming on the heels and without recovering, it you know it, the impact of the virus on the population can be more devastating.
Yeah.
So it kind of builds on itself. Other things that we talked about, that people probably heard, especially here in the Southeast, tick-borne diseases. These things will all spread. West Nile virus, these things can all be kind of related to climate change, which just multiplies the threat. So we talked about that. The basic understanding, burning fossil fuels, right? So oil, coal, natural gas, that is a finite resource. We have to find another resource to get our energy from. However, we can't continue burning it, going on and burning it up, because what we're doing is heating the planet. And one of the main things that fossil fuels emit is one of the most devastating greenhouse gases, and it's CO2. And people go, well, CO2, that's not a big deal. Don't we breathe that out and plants use it? Well, that's exactly right. But CO2 stays around in the atmosphere for a long time. And there's something called the carbon cycle, where CO2 can stay in the atmosphere for up to 1,000 years before it gets recycled back into trees and things like that, or back into coral and things like that. So, and it is one of these things that kind of as radiation from the sun hits the earth, the CO2 in the atmosphere, which is increasing, um, will trap the heat. And we'll talk about that in a minute. But there are a lot of other greenhouse gases. So I hear this from the naysayers, right? Well, water vapor is a greenhouse gas. It absolutely is. But water vapor is constant. Water is constant on our planet, whereas carbon dioxide is not, based on human emissions. Methane is another one, ozone, nitrous oxide. All these things are greenhouse gases, and they all contribute. But the big contributor is actually a relatively harmless gas as far as to us, but not necessarily the planet at a whole, and that's carbon dioxide. We talked about the scientific consensus. Virtually every organization, scientists all over the world are basically on board with this. Science does not move in a straight line. It has bumps, it zigzags all around, and you will have scientists disagreeing on certain things. But overall, that is the nature of science. But overall, 99.9% of the scientists, especially the nations of the world, agree that it is happening, that this is not a hoax.
Yeah, we spoke
And
about that a lot in
yeah,
153.
right, right. And then we kind of hit on, well, why is there such a kind of
Debate.
hoaxing atmosphere with it,
Yeah.
And we talked about the corporate hypocrisy on climate change, and we made it analogous to like what the cigarette industry did, right? So, and we talked about, the just to step back, cigarette industry in the 50s, where they were actually talking about cigarettes being good for you. They help decrease your anxiety, yada, yada, yada. And well before it actually made it to the public, they knew that there were some big problems with cigarettes. As far as cancer and health goes. And also we see the same thing with these big petrol companies like ExxonMobil and Shell and BP. They know the science out there. However, it's trying to move a big ship and knowing what to do and maybe hoping that technology will take care of it, or it will just go away by itself with some unknown thing in our atmosphere that can take care of it. The earth can adjust. Well, that's not happening. And so there's a lot of denial and confusion. And when that gets to the policymakers are not scientists by any means. And as we saw with what happened with this COVID pandemic, it became very political. And now it's become, this has become very political. But the point of that, Bryan, is, the science is clear. I mean, it's just clear. It's not a hoax. And anybody who can present evidence saying that, climate change due to human causes is not due to human cause. Anybody who can present evidence saying that would get a Nobel Prize. So extraordinary claims require extraordinary evidence proportional to that claim. And we have so much evidence saying that this is happening. So anybody out there, any of your climate science deniers, please, if you have some evidence nobody's seen, you need to get it out there, because, man, I'd be thrilled if you were right, and I'd be happy that you got the Nobel Prize. It's nothing new. We know that climate science, or had an idea that this was happening since science started giving us indications, since the beginning of the Industrial Revolution, which is the main cause.
Well, I wonder and maybe you'll know this, Keoni, just kind of what did we measure first or look at first to say, oh yeah, we're having an impact on the climate?
One of the things that we look at is we have temperature data, right? So we look at the temperature data and we look at the trends, and we see that there is a temperature rise. I think right now over the base temperature of about, I think it's 59 degrees on the planet, right? And that's kind of the base temperature. And we actually have had a 1 degrees Celsius rise, or 1.8 degrees Fahrenheit, and with temperature measurements over 100 years. So we have to ask, like, okay, why is this happening? Are there any things that we can say that are due to natural events why this is happening, right? And so we kind of correlate that with, okay, well, it looks like what is also rising is CO2 emissions. We can measure that, and that's rising. And those two curves kind of go hand in hand. And then we have to rule out, well, could it be anything else? Like we said at the beginning, climate science is very, it's kind of a moving system with all these variables, and you have to make sure that you rule everything out to make sure that it's just not, that maybe it's not a human caused problem. Could it be wildfires? Could it be droughts? Could it be, normal fluctuations of sea ice melting? Could it be the polar ice caps melting? Could it just be, what else? Could it be fluctuations in solar radiation and all that? And so and that's what we have to do when we have climate denialism. We have to make sure that we rule all that out. Could the warming be natural? We need to rely on objective data. And so we have, based on like ice cores and looking at geological data that can go back quite a while, we have a pretty good idea of the fluctuations of Earth's climate. And it does fluctuate, and there's no doubt, but it usually fluctuates due to things like solar radiation. It could be, where the sun emits more radiation and then reduces that radiation. It could be due to, it's actually can be due to where the Earth is in its, spin around the sun. The Earth can go into more of an elliptical type orbit as opposed to a circular orbit, and it can go back and forth between there. The Earth can wobble and tilt, right? So that will change climate,
Sure.
warming and cooling. And then, believe it or not, there's like 26,000 year cycles where as the Earth relative to the rest of the Milky Way galaxy rotates, right? And you know, if you took snapshots of the sky every 26,000 years, it would look a little bit different based on where the Earth is relative to the rest of the Milky Way. And and so that even I forget what the name of that is, but based on where it is in the Milky Way and based on, you know, the pool of different planetary bodies on the Earth,
Right.
especially the sun, you get these things. So you need to rule all that stuff out as opposed to then just the natural things that happen on the planet.
Right. And the experts have done that is the point.
The experts have done that, and that is not something that, you know, I would even know how to begin to do.
Yeah.
Unless I went to school for that.
Yeah, absolutely.
So, but I wanted to bring that up because there's a lot of things.
Right.
So the main thing is global warming just another natural event? That's the main question we have to ask. That is the main thing the climate change deniers say. They just say, well, the Earth has warmed and cooled many times in the past, and this is natural. It absolutely is natural. However, the climate system is very complex, but it's still deterministic, meaning that any significant change must have a cause. We ought to be able to find the cause. So you just can't say, okay, well, we have this fluctuation without determining a cause, right?
Yeah. I
Um,
mean, if you think of it like an aquarium in the biosphere that we live in, we've added new organism, us, and then what we've created in this biosphere. And the biosphere is kind of changing around us, like you alluded to. We, you know, the aquarium could be on the desk, which is right under the vent, or the aquarium could be on the
right.
dresser, which is near the window where it's a little warmer, all sorts of things like that. But really,
Yep.
we're finding the importance is what's happening in the aquarium.
Right. And where it is relative to space,
Right.
right? And how that affects things. Um, you know, we have to find evidence for a convincing cause,
Right.
whether it's caused by humans or not. We still have to find that evidence. So um, Jack Gibbons gives the analogy, you know, so humans have often died in the past from natural causes. Therefore, a man with a knife sticking out of his chest must have died from natural causes. You know, that's kind of the argument that people are making. You can't do that. You know, if the knife is sticking out of his chest and he's dead, you're probably going to say, well, it's probably the knife that killed him, not natural causes, you
Mm-hmm.
know?
Mm-hmm.
And that's kind of what we're saying here.
Right.
So there's been a lot of different natural causes for warming and cooling events. We have that solar output, asteroid strikes, mega volcanic eruptions. And then I was talking about like the orbital
Mm-hmm.
variations. There's a scientific name for that called Milanovic, the scientist who came up with these. Um, and anyway, it's just the orbital variations based on planetary objects and where Earth is in space within our own solar system and within our own galaxy. And that can also have, causes. So, but the main cause would be to really rule out, I would say, and this is what he did in this book, was say, well, okay, well, could the sun be causing it? Well, we know the sun is a variable star, meaning it's a magnetic variable star, meaning that it does have increases in solar radiation that can warm up nearby planets, and then it also has decreases, you know, and that again, that can be due to the sun itself. It can also be due to where the Earth is in terms of its position, overall position. And if people really want to look at this, and we have data on this to see if there's any correlation there, and we have data between 1880 and 2019 between solar activity and current warming trends. And if you want to just Google Earth's temperature versus solar activity and go to Google Images, and you can see the graphs for that. All right. And see what's going on there, and see that as we get closer to, the latter 20th century and into the 21st century, we see that there's really not a big correlation there at all. but yeah, Google Earth's temperature versus solar activity. So there's no upward trend in the amount of energy hitting the Earth. So we have data on that. So there's no increased solar energy hitting the Earth. So that's a smoking gun number one. So we have that data. Then smoking gun number two, if the sun was responsible for global warming, we would see warming throughout all the layers of the atmosphere, right? So if you have a sun putting energy into this closed system, like your,
Yeah, like that
terrarium,
aquarium. Yeah.
or the aquarium, you would see all layers of the air, right? You have different layers of our atmosphere on the Earth. They would all kind of heat up at the same time, okay? And what we actually see is that this is not actually happening. So warming does not occur all the way up through the atmosphere. What we see is warming at the surface and cooling in the upper stratosphere. And this is consistent with warming being caused by heat trapping gases, right? So it only goes to a certain extent. So you see variation there. So there's some data there. So also another thing to think about is nights are warming faster than days, and winter is warming faster than summer, which is predicted by heat being trapped in the atmosphere rather than increase in solar radiation, which would cause day and night and the seasons to warm evenly. So that's another common sense way of thinking about it. But the data's there, the objective data is there if you just Google Earth's temperature versus solar activity. Another question to ask is the current global warming a result of natural variability? Many components cause the climate system to be very, very variable. You get rainfall, you get the extent of the Arctic sea ice, the increase of it and the contraction of it. There's normal fluctuations called El Nino, which are warming events, and these tend to be evened out with El Niñas, cooling events. Those are all normal fluctuations. If you Google, you can see an image on, just type in global temperature reports, and what you see is, when you look at the data there, is that there's really no apparent natural cycles in the observational record that can explain the recent changes in climate. Yeah. So and in addition, the natural cycles within the climate system can only redistribute heat. They cannot be responsible for the observed increase in overall heat content of the climate system. All right. So we are seeing that, right? We're seeing the Earth slowly heat up.
Okay.
Yeah. So solar flux and weather variation do not correlate with what we're seeing. But what does correlate with what we're seeing? The increase in greenhouse gases. There's no alternative explanations for it. We see the increase in the greenhouse gases, especially CO2. We don't see any increase in solar flux, or, we can rule out, the Earth's position and its axial tilt and all that, the astronomy behind it and where it is in position with the rest of the planets and all that. We can rule all that out and how it's rotating. And we can do, and that's very easy to do. And that's what scientists have done. So based on that and what we just explained, climate denialism, so far it's fails. It's just completely not a good thing to bet on, right? And it's certainly not a good thing to bet on when there's no planet B. This is our only planet.
Right.
Right. So the evidence for natural cause global warming is lacking, but the evidence for anthropogenic cause global warming is compelling, with the CO2, the burning of fossil fuels, and all that. So it's also unprecedented too, right? There's never been anything that we know of where the Earth has warmed 1 degree in the, and that's a big increase in warming, and done it in just 100 years. We've never seen that or have data for that when we look throughout history. I mean, the Earth has definitely warmed by more than 1 degree, but it usually took, thousands to millions of years to get there.
How far back are we able to kind of date our temperature and that sort of thing? The kind of like the testing of the soil. How much can we find out about the atmosphere and the overall early Earth?
Well,
as far back as can we go?
I'm not quite sure. We can go back pretty far. I'm thinking with geological data, we can go back far, but it
So
makes
more
me
than one of
think.
those 26,000 cycles,
Oh
correct,
yeah,
Bobby? Yeah,
yes,
quite a
yeah. I
few of
mean,
them.
you can go back a few glacial ice ages.
Hmm.
You can go back quite a few. So I'm thinking, those cores can go back at least 50,000 years. You can go, those ice cores can really tell us what was going on in the atmosphere at that time. And I think those are pretty important. I think there's many other
Yeah.
ways to do that too. I mean, I'm even thinking with you could even like get an idea with fossilized trees, tree
Hmm.
rings. I mean, these things are all part of the carbon cycle, right? You could probably get a good idea with, gosh, I would even think coral to some extent. But again, I just know like ice cores are a big thing about getting an idea of what's going on
Yeah.
with it, and
Yeah.
they go back far.
Yeah.
I don't
So
know
the
if they
point
go
is,
back millions of years, but they go back hundreds of thousands of years. I'm almost certain of that.
right. So it's not when, 1600 AD when we start writing down the temperature or anything like that.
Right, right.
Consistent weather, man.
Right, right. I mean, as far as that data goes, we're talking 1800s to the present,
Okay.
as far as like
Okay.
getting consistent temperature data. But we can get an idea and make, um, good guesses about what the temperature was in the past. I mean, we know that in the past that the Earth was at one point millions of years back was nothing but a frozen snowball.
Right.
You
Yeah, we can
know,
get a lot of information about
we
the
right
biosphere that we're
we
talking.
also know, you go back even further, it was a molten lava ball way back. We also know that at some point, um, probably when the dinosaurs roamed, that most of the earth was very tropical. So we have that data, and we know that. We know what happened based on an asteroid or volcanic eruptions causing extinctions and climate change events and what they do to that.
Hmm.
We also have an idea what tectonic plate moval does to the
Hmm.
climate too. So, but that's all pretty easy to look up. Like, you can just Google that pretty easy and see that, we can get a lot of good data that goes back really, really far and get an idea
And it's
of
many,
where
many,
we are.
many groups of varying types of science that help bring all this information together. So
Oh,
just
from all over the
about how we
world.
talk about kind of conspiracies and whatnot, where it's
Oh, absolutely.
believable, not hush hush here.
And that's a great point. You're not talking about just climate scientists saying that this is happening.
Right,
You're
right.
talking about, people
Get a
that
lot of
are
input from a
plant.
lot of
Yeah, you're
educators.
talking about plant scientists. You're talking about people who study, the rotation of planets. I mean, there's a lot of disciplines of science that have come together that are coming to the same conclusion.
Mhm.
So yeah, that's a really, really good point. Um, and so if we've increased the temperature, by 1 degree Celsius or 1.8 degrees Fahrenheit, the trend seems to keep going up. And one of the things that a lot of climate scientists are in panic mode about is, we we are going to have some devastating consequences, more so than we're seeing now, if the trend keeps going up. And like I said at the beginning, we're talking about, like this current pandemic. I see it as, at least in part related to climate change. All right,
Yeah.
the current pandemic we're going over. And then also, all the wildfires that are increasing all over the world. That is a direct result of this increase in temperature also that's going on. And then the consumption of fossil fuel, which is not slowing down. It will be interesting data based on like how the world kind of slowed down with the pandemic, where it may have cut down some of the trend, but the trend is so far, it's still, I think it's still going up, but we'll see what's going on. But we do know that to really stop the trend, we have to, really cut fossil emissions close to net zero. I mean, that's a critical first step. And how we do that, I mean, that's something we can, me and you can talk about on this podcast, or we get an expert on to see what are the kind of the solutions to that. And that other book I talked about, Drawdown, at the beginning goes into a lot of the solutions that can help with that. And there's some pretty neat solutions. And I think, you know, using technology and using our ingenuity and all that, I think we can, and just bringing the world together and countries together to hit these targets of reducing fossil fuel emissions. I think, you know, we're still going to see a lot of issues that are going to be happening. Probably they will continue to happen well within our lifetime, but you know, we can start seeing the downward trend and start seeing some benefit. I'm hoping by 2020, by 2100. So we'll see.
So hold on, 2100.
Yeah, right. So based on the modeling, and again, models are just, you know, they're kind of, you know, making a best guess, but based on the modeling, an increase of 2 to 3 degrees, which the scientists seem to think will hit, is we're talking about sea level rises of close to 100 feet, wildfires like ravaging large parts of the earth, droughts causing widespread famine. I mean, you know, millions and millions of people being displaced, and then pandemics, diseases, so on and so on. And so, you know, the science is clear. I mean, it's pretty darn clear. And we have to do something about it. And you know, I even feel like I don't know if you feel like this, Bryan, but I feel like, you know, that I'm thinking back and seeing what we're going through now. And it may be my bias or whatever, but it certainly seems tangible to me. It seems like it's in my face now, you know, just experiencing the seasons, experiencing the heat waves, you know, seeing what's on the news and stuff. And it's starting to, I think, impact everybody.
Yeah, I know we talked a little bit about that in 153 in more detail.
Yeah. So that's the basis of it. But I just want to, for some of you physics geeks and stuff like that just want to know, okay, that's fine, all well and good, but tell us, you know, kind of the basics of how it works. So the basics of global warming and the physics behind it, right? So I'm going to try to explain this as best I can. You know, I probably may miss some things, but and Bryan may correct me if I'm wrong with some of this, but I'm just going to go through it. But I think I can explain it in a basic way that people can get a better idea. And if you think back to your high school chemistry, physics class, college classes, I think some things will come together where you can actually talk about climate change when you're confronted with somebody who's denying it in kind of a more intelligent way. All right.
Yeah.
So what do we know? We know we want to talk about heat and heat transfer. And to do that, we have to know what the concept of atoms and molecules are. And we know that atoms and molecules make up gases, liquids, and solids. And heat basically just depends on the speed of the atoms and the molecules. So think about boiling water, right? Think about taking it from an ice cube to water to boiling it. Okay. Basically in the ice cube, those molecules aren't moving very much. There's very little heat coming off the ice. You know, with the water, there's more heat coming off of it. And then once you get to steam, there's a lot of heat coming off of it because those molecules are moving very, very fast. So the faster you move molecules, the more heat that you generate. All right. And then so heat transfer can happen by a number of ways, by conduction, convection, and radiation. And heat always goes from warmer to cooler. So conduction occurs when two objects at different temperature are in physical contact, right? So think about an ice cube on a table, right?
Ice that pack ice on cube, you.
Yeah, right. There you go. The ice pack on you, and how you know both the temperatures equilibrate over time. And they're actually in physical contact. And convection occurs in liquids or gases, or when warmer areas rise relative to cooler areas and are replaced by cooler areas. So convection is a critically important part of the Earth's weather system. So as the surface of the Earth heats up, right, it will warm the air, you know, close to the surface, but warmer air rises and then it's replaced with colder air, right? It's kind of like a cycle. Colder air comes to the bottom and then that heats up. This is how weather systems, the basics of weather systems. Warm air rises, cooler air drops, cooler air rises, the warmer air got cooled up top, and it just creates a cycle, and it creates what we feel out in the world, like of wind and, you know, to some extent waves and stuff like that. And these are part of the solutions for cooling the planet down, like harnessing that energy through like turbines and things that generate, you know, with the motion of waves, can grab the energy off of that, and instead of using fossil fuels. So we can do that. The other way is through radiation, and that's just heat being transferred through empty space. And you think about electromagnetic radiation, also like our sun. That's how the sun heats the planet, through electromagnetic radiation. And all objects emit radiation. Okay, so stars, planets, humans, all objects do that unless you're at absolute zero degrees Kelvin. Okay, so and that radiation, you can think about it as, when you talked in chemistry and physics, it's like you're emitting photons or you know, radiation. And when the sun emits radiation photons, they hit matter like the earth, and thus can raise the temperature. So sun to earth radiation, that's a good example of that, the sun heating up the earth. You know, think about then as it hits the earth heats up. Now you have the ground heating up the air, that's conduction. And then you have heat rising and replacing cooler air, that's convection. Right. So you can see that. There's cool graphs of that. You can think about that. You can just type into Google heat transfer via Google, you know, or global warming heat transfer. You'll see all cool kinds of graphs with that. So hopefully that makes a little bit of sense, and you know, that people can just wrap their head around what that is and what heat transfer is. The next topic I want to talk about is just the electromagnetic spectrum. So yeah, do you remember this from your physics, the Roy G. Biv? Do you remember that abbreviation?
Not that abbreviation, no.
Okay, well, it's a mnemonic. It's basically a mnemonic for visible light. So Roy, R is red, O is orange, yellow. So when you look at the visual spectrum of light, how it breaks up into the rainbow, it's Roy G. Biv.
Okay, yes.
To ring a bell now?
Now I know.
Okay. So red, orange, yellow, green, blue, indigo, violet, right? That's the visible light spectrum. That is the light that actually gets to the earth. All right. That's the visible light from the sunlight. And it lies along a spectrum of electromagnetic radiation. And that electromagnetic radiation spectrum, on one end is radio waves, and on the far end are gamma waves. And then kind of in the middle, you have visible light, sunlight. And on each side of visible light, you have infrared, and then you have ultraviolet, right? So after the Roy G. Biv violet, you get ultraviolet, and right before the red, you get infrared. All right. The higher the wavelength, the more energy that you're getting.
Right.
Okay. Yeah. So, all right. So, and I should say, the smaller the wavelength, the more energy the wave has. So anyway, so all of the sun's radiation in the visible spectrum, which is a very small part of that electromagnetic radiation spectrum, penetrate the atmosphere and irradiate and warms the earth. And without any human contributions, the earth with that alone will be stable at about 15 degrees Celsius or 59 degrees Fahrenheit. And it stays pretty stable. As it hits the earth also will emit back to space some light. So it will bounce stuff back off into the atmosphere or into space to get rid of some heat, right? However, if there's a lot of greenhouse gases there, those greenhouse gases will absorb that energy and keep the heat trapped.
Right.
All right. So, and we know through the first law of thermodynamics, energy in equals energy out. A planet like the Earth in thermodynamic equilibrium must radiate back to space the same amount of energy it receives from the sun. If the planet doesn't do that, then what's happening? It just keeps getting warmer and warmer, right?
Right.
Right. So, so the Earth is transparent to incoming solar radiation. So a lot of that will get to the surface. So does that all make sense for the most part?
It certainly makes sense of the sun's role and why we're warming and whatnot. And then we have a
Right.
lot more that we covered.
Right.
Certainly covered a bit.
You're right. Right. So there is actually what we call an atmospheric window where, as that radiation from the sun hits the earth, right, it gets reflected back out to space in the form of longer wavelengths in the infrared spectrum, right?
Okay.
So if we were an alien civilization looking at the earth, we would be able to tell based on the glow of our planet, we could be able to get an idea. This is fascinating to me. If that planet is a carbon based subording planet, basically burning fossil fuels, they'd be able to tell based on, if they had enough data, if we were burning fossil fuels, on what that glow, the infrared glow of our planet looked like.
Interesting. Wow.
Yeah, it's pretty fascinating. So we are a fossil fuel carbon based planetary civilization, and we want to get away from that
Right.
because we're just heating up the earth.
Plus,
So
we're
anyway,
sending the signals for Independence Day. They're probably on their way.
right, right. Oh yeah, they'd be able to tell. If somebody was watching us, they'd be like, yeah, they are. There's most likely intelligent life forms there, and they I hope they know what they're doing because they're burning themselves up.
Yeah, it seems like idiot life forms.
Yeah.
From this distance, it seems like idiocracy is going on down there.
Right. It's exactly right. So anyway, so I talked about that atmospheric window where we can get radiation back out, so basically the Earth can get rid of heat dump back out into space through that
Mm-hmm.
atmospheric window. And so there is some of that, and the Earth has some built-in mechanisms to help promote that, right? And one of
Right.
them we briefly talked about was the Earth albedo effect, or its reflectivity effect. So all incoming solar radiation, it's it gets to the Earth. It's not absorbed by atmospheric molecules. It reaches the Earth's surface. Some of the rays are reflected directly back out to space without warming the planet. Okay, so it doesn't. So this radiation doesn't go all the way to the planet. Some of it gets reflected back, but the overall uh, reflectivity over time for reflecting things back is about 30%. All right. So we have clouds that reflect things back. You have aerosol particulates. You have bright colored areas of the surface like snow, right? So that's
Mm-hmm.
why we talked about if the polar ice caps and,
Yeah.
there's no more snow on mountains and stuff, that makes it worse. You can think about this if you ever think about how bad you can get burned if you go ski on a nice sunny day and and it's cold out, but that snow, the radiation's reflecting back in your skin, you get burned really bad from that. And snow, it reflects almost 100% back out. Whereas ice, not as much, and water certainly doesn't. Water can actually will reflect some back out, but will absorb some energy too.
Yeah.
So that's a concept that people need to know, the albedo effect. So as we lose snow and the polar ice caps and glacial melts and stuff, the Earth is losing its capacity to maintain a stable temperature.
Right.
So far so
What do we
good.
do, Keoni? Yeah.
Okay. um. So okay. So then, how does solar radiation actually warm the Earth's surface? So let's just talk about that a little bit. All right. So we have light that can be light. You've heard light can be thought of as like a particle and as a wave. You've heard that before,
Mm-hmm,
right?
mm-hmm.
Yep. So, all right. Well, anyway, you can think about solar radiation coming to the Earth, and it's traveling to the Earth in the form of a wave. You can think about it that way. But as soon as it hits the Earth, you can think about it as kind of like a particle hitting the earth and causing the other particle molecules on the earth's surface to vibrate. And we just talked about, like, anything that vibrates more than it normally would, what happens? It heats up.
Right.
Okay, so the earth's ground will heat up. If the earth's ground heats up and we don't have a way to dump the heat off, then you kind of get this vicious cycle.
Mm-hmm.
And so that's kind of what's happening. So surrounding molecules, as they vibrate more, tend to warm up the other molecules close by, and so on and so on. All right.
Yeah.
All right. And so now that we know that, so as the earth warms up, it wants to radiate heat back. Now let's talk about greenhouse gases and how this works. So the main greenhouse gas that I want to talk about, and there's a number of them, but we'll talk about three in particular: water, carbon dioxide, and methane. Okay, and I'm sure people have heard all of that stuff, but water is pretty stable. Water gets recycled through the water cycle, the Earth's water cycle, so it's a constant for the most part. It will heat up. The oceans are warming and stuff like that based on global warming, but and it is the most common greenhouse gas, water vapor is, and second to that is carbon dioxide, and then after that is the methane. So we'll talk about those in just a minute. One of the things about these compounds in the atmosphere is they can all kind of trap the radiation coming off the Earth's surface to a certain extent. And the molecule that does it the best is CO2. It can trap it really, really well as CO2 rises in the atmosphere, and it can put it back on the Earth, just adding more heat to the fire, so to speak.
Right. Mm-hmm.
Whereas water doesn't do that, and water kind of maintains that atmospheric window that we talked about, where radiation from the Earth's surface can go back out, whereas carbon dioxide kind of closes that atmospheric window a little bit. Again, adding fuel to the fire.
Right.
All right. And so basically you get the heat coming off, going to the carbon dioxide basically traps it. You get the greenhouse gases. It can reflect it back to the Earth. Also, once carbon dioxide heats up, what happens to that? It moves faster, right? So carbon dioxide now can bounce off other molecules in the atmosphere. Like, what's another big one in the atmosphere? Well, H2O is big in the atmosphere. Nitrogen is big in the atmosphere. Oxygen. Anyway, you can excite all those too and heat those up. And just that motion can heat up, and you get and because of that, what does that bring to mind? You may get more extreme weather events on that alone.
Right.
So two methods, right? So sun hits the earth, CO2 or the greenhouse gases trap it, bring it back to the earth, add fuel to the fire. And as these molecules heat up in the air, in the atmosphere, they can create more vibrational energy and distribute it across the other molecules. All right.
Yeah.
So we talked about water vapor as the most prolific greenhouse gas, and it is responsible for the most natural global warming, and it's about 70%, but it's constant. Okay, so we can measure that. But water gets recycled through the hydrologic cycle, and a molecule of H2O only remains in the atmosphere about 10 days before it gets recycled into oceans and streams and things like that. It's fascinating to think about, like, the water that is on our planet. It's probably, yeah, it's been here for, it's been here. It was the same water that the dinosaurs drank, so it's kind of fascinating to think about that.
Same one dinosaur peed out too.
Same thing. In fact, yeah, it's fascinating. I mean, in fact, we probably, both me and you, have atoms that were in dinosaurs. So anyway, it's interesting thought
discredited everything we said.
But actually it didn't. Go look that up. But anyway, Where were we? Okay, so water lasts about 10 days. It's considered a constant, so we can kind of take that out of the equation. Also, water vapor keeps that atmospheric window for infrared wavelengths escaping back out to space open to some extent. CO2, this is the most important greenhouse gas. It absorbs the infrared radiation at wavelengths not absorbed by water, close to the center of the wavelength spectrum we talked about. It also mixes with all layers of the atmosphere also, so in the troposphere. So it has a strong absorbing effect all the way through the atmosphere. And the other problem with CO2, it can last for hundreds, even thousands of years before it gets removed from the atmosphere through the carbon cycle. You know, so we talked about how does carbon get removed? Like, well, we talked about plants and trees. Those are big storages. You know, think about a huge tree and how much carbon could be stored in that, or coral reefs and things like that. But these things, carbon, once it's in the atmosphere, at least for our purposes, it stays in the atmosphere. So the more carbon you have out there, the more it's going to trap heat.
Mm-hmm.
The other thing we hear about is we hear methane, right? And methane is one of those that, you know, is a powerful greenhouse gas, but it doesn't last very long. It's very short-lived. And the main problem with it is that it breaks down into the other two greenhouse gases we just talked about, especially water and CO2. So the more methane we put out there, the more CO2 we are contributing. And methane is a natural greenhouse gas, you know.
Yeah, I think we talked about that in 153.
Right. So that's a little bit of the science and physics behind that. And hopefully I explained it in a way that people can understand and get an idea and maybe talk about it and hopefully influence some of these climate deniers that we have out there.
Yeah.
I think next podcast that when we talk about this, I would like to just talk about what are some of the solutions that we're dealing with and what are, you know, really get into the ideas. And I don't know off the top of my head, like what can we do on an individual level that can make an impact?
Right.
You know.
Yeah, we need some hope after this one, Keoni.
Yeah. Yeah. And it really, I think, you know, it really comes down to people coming together and, you know, seeing the need for it.
Right.
So.
All righty. Well, thank you everybody for listening. Thank you, Keoni, for the education on this. It's definitely something I don't know a lot about.
Yeah, well, me neither.
Everyone
so I'm
should.
hoping, yeah, everybody should. I think everybody should get an idea of the basics of what is going on here.
Yeah, absolutely.
You'll have more faith in the science and stuff like that, and things will not be able to get politicized with you like they tend to do here.
Yeah, absolutely. All right, everybody, be well. We'll speak with you next week.
All right, take care, everybody. Thanks. Bye.